Welcome back, students. So in the last video we were talking about the average value, the mean value, and the root mean square value of a function in general, and then we talked about voltage and current specifically, and also power. I'm going to summarize that now, and we'll take this lesson forward from that summary. So if I have an AC source, okay, where V, this V is equal to Vm sine omega t, it changes with time obviously, and then if you connect it to your resistor R, and current I will be flowing through it, and this I itself is a function of time. So as V is a function of time, and I will also be a function of time. So as time changes, this also changes. So here V is written as Vm sine omega t, and then I is written as I at any point in time t is written as Vm sine omega t by R. R is the resistance of the circuit. So which gives you this. If you take these two things, these two constants, and that will become Im sine omega t. So Vmax by R is Imax, the maximum value of the current in the AC circuit, sine omega t. Then we also said that V, the V Rms value, the Rms value of voltage is given by Vm by root 2. And we also said Irms I for this will be Im by root 2. And then the average value of voltage will be 0, and the average value of current will also be 0. Over a cycle, it will be 0. We also did that yesterday. But then we also said the average power is equal to, okay, I'll also write this, V average is 0, and then I average is also 0. What is average power? Average power was V into I, Vrms into Irms, or this was also equal to Im squared with 2 R by 2. This was the other equation, and it was also equal to Vm squared by 2R. So all these are equivalent. This is what we found. And we said if I take these 2 points, okay, take these 2 points, if I measure the voltage across that, this is output of the generator, okay, the 2 points. So suppose this graph, the voltage graph is like this, okay. So this is the voltage graph. This is V, and then this is T. So it's like this. So what does it mean? Suppose this is 10 volts. Let's say this is 10 volts maximum. So it starts from 0, goes to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then starts decreasing from 10 to 0, then from 0 to minus 10, and from minus 10 to 0 again, and then the cycle repeats. That's what we said. So at any point you see, at any point in time, now I take the output. If I look at the output now, at this second it will be say 1 volt. Then after say 0.1 second it could be 2 volts. Then after some time, with 3 volts, 4 volts, 5 volts, 6 volts. So the voltage across these two terminals will be changing. Okay? And as the voltage changes, I have a resistance connected to that, so the current will also change. The bigger the voltage, the bigger the current. So the current will also increase because I have a resistor here. So the current, I will close this loop, so the current will flow. As the voltage increases, the current will also increase. So for 0 voltage, I'll have 0 current. For 1 voltage, I'll have some current. At 2 voltage, I'll have some more current. At 10 volts, then it would be the maximum current I'll get. And as it reduces, then the current will also reduce. So this graph, the current graph, will be same. As this is 0, as voltage is 0, current is 0. This is voltage, and this is current. Right. As voltage is 0, current is also 0. As voltage is maximum, current is also maximum. When the voltage is minimum, current is also minimum. Meaning that the current is flowing in the opposite direction. It is maximum in the opposite direction. That is why we call it as alternating current. When the direction changes, that is what it means. So you get this graph. Okay? This is fine. This is for resistance. What will happen if I connect an inductor to this circuit? So now the question is, what will happen if I connect an inductor to this AC source? Here I have connected a resistor. I am going to connect an inductor to it. Okay? This is what I am going to do. I have the AC source, V is equal to Vm sine omega t, and I'm going to connect an inductor. A value L. So clearly a current I will flow through this. Nothing is a pure inductor, because an inductor has to be necessarily made of a conductor. You have to, if you make a coil, again you need a conductor to make a coil. So clearly a coil will have its own resistance. A metal will have its own resistance. It could be a very small resistance, but it will always have a resistance. So in all practical cases, you will also have a resistance associated with it. But I am not going to consider that resistance. I am going to consider a theoretical inductor, a pure inductor, which doesn't have any resistance, which doesn't exist. But to simplify my analysis, I am going to consider only the inductance. Well, you can even think of this as an inductor made of superconductor. So superconductor will have zero resistance. So if you make a coil out of a superconductor, or keep cooling it, so keep that as a superconductor all the time, then you will only have inductance. You will not have resistance at all. Imagine that you have a situation like that. But the general point is that this is a theoretical inductor which does not have any resistance. Practically, you can make a superconductor based inductor. Okay? In that case, you will have only inductance. Anyway, this is for our analysis purposes. Okay? And that is why we are considering only the inductor and the inductance of the inductor, not the resistance also. Okay? So this is what we got here. Okay? So what happens is that this AC source will send a current, will try to send a current, and that will try to set up a flux. And since the current voltage is varying, the current will also vary. As the current varies, and this will start opposing that change. So there will be an EMF, a back EMF. generated in this coil, and that will oppose this change in current. Okay, and that I call that induced voltage as VL. VL is a voltage that is getting induced across, let's say, across this. Okay. So you have V here and you have VL here, and then you have a loop. So Kirchhoff's voltage law must be obeyed. So what does it mean? It means that at every end, all points in time, this voltage must be equal to this voltage. If this is 1 volt, this must also be 1 volt. This Kirchhoff's law has to be obeyed. If it is 10 volts, then this should also be 10 volts, because Kirchhoff's law must be obeyed. So the total voltage difference in a closed circuit is 0. So that should be obeyed at all times. So what I will say is that using Kirchhoff's law, this V plus this VL must be equal to 0. So this is okay. So and this should also oppose it. If this is plus, minus, and this should be plus and minus. It should oppose that. So V plus VL equal to 0. Like a resistor, you see. That's what you do normally. Resistance. If this is positive, negative, it should also be positive, negative. And that should happen all the time. If this is positive, that is negative, this will be positive and that will be negative. That will also happen. So Kirchhoff's law must be obeyed at all times in this circuit. So V plus VL must be equal to 0. But what is VL? VL, you know that minus L to di by dt. So that's EMF induced. It should be minus L di by dt. So if I substitute it here, then I'll get V minus L di by dt is equal to 0. And what is this going to give me? And this is going to give me V is equal to L di by dt. So I just take di alone, the change in current. So di is equal to V by L to dt. Okay? So the change in current is this, delta I. And how would I calculate the current at a particular time? I integrate. This is a change. So change. So at this particular point in time, what's the current? The sum of all the changes. At any point in time, the current is going to be equal to the sum of all the changes. So I need to go for integration. So I'm going to integrate this. Okay. So but what is VL dt? So this V by L dt. Okay, it's going to be V m sine omega t dt by L. That's integration. So Vm is a constant, the maximum value of the voltage, and L is also a constant, the inductance of this coil. So I just remove them from inside the integration. Then I'm going to get Vm by L integral sine omega t dt. And what is this going to give me? And this is going to give me minus sine omega t will be minus cos omega t by omega. So I will get minus Vm by omega L into cos omega t plus c, and that would be my I. So current at any point in time is given by this equation. Okay. So if I apply limits, then the C will be gone. The other thing will get the value for the current. So anyway, so that's the current. This is what I found as the current. Okay. Well, I can compare this with this equation. Okay, I'm going to compare that with this equation. You see, Vm by R, you treat it as Im. So then sin omega t is taken out. So here also, if I do that, cos omega t can be taken out, and then Vm by omega L, I can consider that to be Im. It's very similar, which means that omega L plays the role of R, right? We know this because sin omega t is a ratio. So, you know, one value by another value of the same quantity, right? So, this has no units, and only this has units. Vm by R is amperes, right? Volts per ohm is amperes. So, this won't have any unit. Likewise, cos omega t will also not have any unit. So, Vm by omega L must be equal to I. So, Vm is voltage and omega L must be resistance. So, I can say that this omega L, okay, has the attributes of a resistor. It acts like a resistor in this case. This omega L. Okay? So, I will call that as XL. XL is equal to omega L. And this is called as XL is called as inductive reactance, not resistance. Inductive reactance. That is your XL. Okay? So omega L is equal to XL. XL will have attributes of a resistor, a resistance R. So this XL is called as inductive reactance because this reactance is given by the inductance of the coil. So it's called as inductive reactance. And what would be the unit of this? It would be ohm, obviously, because R, this is like R. So omega L will have the units of the resistance, like that's ohm. Okay, so the unit of this will be ohm. Hope this is clear to you, then we will continue. Okay, so I'll write this. I is equal to Vm by omega L minus, right, minus Vm by omega L cos omega t plus C. So this is what we found. But the value of C will be 0. The reason is because this current is oscillating with 0 as the middle point. 0 goes to the peak and then comes back, when the negative peak or valley, then comes back to 0. So you see the constant would be 0. It doesn't get shifted or something. Okay? So the constant value will be 0. Even though I have C here, because it's a sinusoidal curve, the constant value will be 0 in this because you're not shifting it. It's not that it's moving, going from say 2 to 10, then to say minus 8 or something. So it starts from 0 and then it goes to 10 and then it comes to 0, so minus 10 goes back to 0. So the constant value would be 0. Okay? If you require any further clarifications on this, then I'll do it separately. But take it that this constant must be 0 because it is oscillating with 0 as its center. So there is nothing that is getting added to it. Okay? So it is 0. So I'll say that I is equal to minus Vm by omega L, then cos omega t, because that is 0. Okay. Okay, and we also said that this I is equal to minus Im and then cos omega t. Okay. So notice I want to handle this minus cos omega t. So I take this Im and then minus cos omega t. I want to handle it. So what is minus cos theta? It will be sin theta minus 90 degrees. Okay, so you have the trigonometric identity. It says minus cos theta is equal to sin of theta minus 90. Right? So that is what I'm going to use now. So I take minus cos theta minus cos omega t must be equal to sin of omega t minus pi by 2. So I'm going to use this in this expression. So my I now becomes Im and sine of omega t minus pi by 2. So this is expression I have for current. Current at any point in time t is given by this expression. Im, maximum value of current, and sine omega t minus pi by 2. Notice that this is not the same as the one you had for resistance. For resistance, what did you have? For resistance, you had I was equal to Im sine omega t. But here notice that is sine omega t minus pi by 2. And in both cases, the voltage V is Vm sine omega t. Here also, V is equal to Vm sine omega t. So this is what we started with. If V is equal to Vm sine omega t, I is Im sine omega t minus pi by 2. But in the case of resistance, it was Im sine omega t, which means that this had its maximum when this had its maximum. If sine omega t was 1, then V was Vm, and if V was Vm, then I was Im, because sine omega t was 1 in that case. So that is not the same here. Notice here, if sine omega t is 1, which means that omega t must be 90 degrees, right? Omega t, if omega t is 90, then V is equal to Vm. But what happened here? If omega t is equal to 90, pi by 2 minus pi by 2, it will cancel, then it will be sine omega's sine 0 will be 0, so I will be 0. So when the voltage is maximum, the current is 0. And when the current, or when the voltage is 0, okay, suppose it's 180 degrees, okay, what is 180, which is pi, so I have, this will be 0, voltage will be 0. But if I put pi here, pi minus pi by 2 will be pi by 2, this will be 1, so I will be Im. So when the voltage is 0, when in this case, then the current is maximum, and when the voltage is maximum, the current is 0. And what happens when sine omega t is 0? In that case also, the voltage is 0, but if this is 0, then you get sine minus pi by 2. So you get minus 1, so you get the value here, not the peak. The negative peak is what you get here. I is equal to minus Im. You can see in this that the current is kind of lagging the voltage. When the voltage is 0, suppose the angle is 0, sine omega t is 0, when this is 0, then this is actually minus Im. When this is 90, then it becomes 0. When this is 180, then this becomes positive maximum, for the positive peak, you should say. So you can see that this is kind of lagging behind the voltage. I'm going to draw the graph now. So this is my time. Okay, so this is time. This axis is the time axis, and this is the axis where I have voltage, and I will also mention current. I'll have two graphs for the same thing, for the same time. Okay, so let me take the voltage graph now. So this is my Vm, and I'll say this is my Im. Okay, likewise this is my minus Vm, and this will be my minus Im. Okay, so I'll start from 0. Then the voltage reaches its peak here, and then becomes 0, which is negative peak, which is 0, and then continues. I'm doing it for one cycle, so that gets repeated. Okay. Let's copy it. Okay. So it goes like that. This is the voltage graph. This is my V graph. So I'm going to draw my I graph now. You see, when angle is 0, so V is 0, but when omega t is 0, the angle is 0, at times equal to 0, then what happens is minus pi by 2. So I have a negative peak. So, and when this is 90, this is 90 minus 90 is 0, so it will be 0 here. Okay? And this is 180, this is 0, but this will be pi by 2 maximum. Okay? And this is 270, so this will be 3 pi by 2 minus pi by 2, you get 2 pi, so you get again 0. And 0. So notice that the current is doing this. Not here. Okay, not here. See. Okay? So this I am. Okay? It's like that. So you can see that this is the current. Right. You can see that it is lagging. So you say that the current in the inductor circuit lags the voltage by 90 degrees. If it's a pure inductor, there is no resistance there. If it's a pure inductor, then the current in a pure inductor circuit lags the applied voltage by 90 degrees. Here, there is no such lagging. If this is maximum, that is also maximum. This is minimum, that is also minimum. This is 0, that is also 0. There is no lagging in the case of a resistor circuit. In the case of an inductor circuit, if this is 0, this could be negative maximum. And if this is maximum, this could be 0. And if this is 0 here, it could be positive maximum. And if this is negative maximum, this could be 0. You see, then it is like this is going first, and this is trying to catch up with it. First it reaches the maximum, then it reaches the maximum. Okay? First it reaches 0, then it takes a little more time to reach 0. Then first it reaches maximum, then it reaches maximum. And first it reaches this 0, then it reaches that 0. Then first it reaches this maximum, this minimum, I should say minimum, and then it reaches its minimum. So you see, it is lagging, it is like coming behind the voltage. So in an inductor circuit, you say that the current lags the voltage. Okay, so that is, I want you to understand this. Okay, fine. So if you understand this, if you understand that in an inductor circuit, current lags the voltage in an inductor circuit, in an inductor circuit, current lags the voltage by pi by 2 radians or 90 degrees. Okay? Okay. So if you understand this, then we'll talk about the power in the inductor circuit. Okay. So what is power? Again, we have instantaneous power and also the average power. So what is instantaneous power? Instantaneous power is the power at that instant, right? So we did that for resistive circuit. Now we're going to do it for inductive circuit. So instantaneous power, P of t, is equal to V at the time and then current at the time. In this case, V at any particular time is Vm sine omega t, and what is current? Im into sine omega t minus pi by 2, or I can write this as minus cos omega t. This can be written as this, right? Minus cos omega t. So I'll write this as Im minus cos omega t. The same. I should write either this or this. This is the same as this, so I'm writing it that way. So that gives you minus Vm Im, then I get sine omega t to cos omega t. Right? Okay. So this sine omega t plus cos omega t, sine theta cos theta form, so I can reduce that using a trigonometric identity. If I multiply by 2 and then divide that by 2, then I get 2 by 2. Then 2 sine omega t cos omega t is actually sine 2 omega t. Right? And then I can take the other things here. So go to minus Vm Im by 2 into sine 2 omega t. So that is the instantaneous power. Then what is the average power over one cycle? So the power over one cycle is this. P average is equal to 1 by t, integral 0 to t, E of t dt. We know this, right? Okay. So if I apply this to this, apply this function to this one, I'll get minus Vm Im by t, integral 0 to t sine 2 omega t dt. But what do we know? This integration will give you 0 as the value. We know that. The average value for the sine function will be 0. So the average power of an inductive circuit, see, because this is 0, the average power is 0. So there is no average power over in an inductive circuit, because the average power over a cycle is 0. So this over cycle is 0, then every other cycle is 0. So the average power is 0 in this. But that is not the case with the resistive circuit. The average power here was equal 2 Vm Im by 2, right, or Im square R by 2. That's what you got in this. In the resistive circuit. So that's the difference. The difference is that in an injective circuit, the average power is 0. But in a resistive circuit, you had some average power. There was some energy loss. But here, there will be no net energy loss in a pure inductive circuit. There is no I squared R loss, I squared C omega L loss. You never have that. The average power in inductive circuit is 0. So when you compare an inductive circuit with a resistive circuit, there are two things that stand out. One is that in an inductive circuit, the current lags the voltage, going behind the voltage. The voltage reaches its peak first, and then the current reaches its peak. The voltage becomes 0 first, and then the current reaches its 0. It lags. Whereas in a resistive circuit, that doesn't happen. The current and the voltage are hand in hand. When that reaches its peak, voltage reaches its peak, current reaches its peak. And voltage reaches 0, current reaches 0. So they're hand in hand. But here it is not so. One leads and the other follows. And the second point is that there is an average power, there's a net average power in a resistive circuit. You get this Im squared R by 2. But here you don't get that. The average power in an inductive circuit is 0. Okay? So I want you to note these two differences between the resistive circuit and the inductive circuit. Now I want to explain the average power being 0 in the case of an inductive circuit through a graph. You may recall that we did the same thing for resistive circuit. Now we will do it for the inductive circuit. You can see that there are two graphs, one in black, another one in red. The black one is the voltage graph. Okay, so it starts from 0 and then goes to peak. Then the cycle repeats. It's a voltage graph. And the red one is a current graph. You can see that it is lagging the voltage. When this is 0, this is a negative peak. And when it is when first this becomes 0, then this becomes 0. First this becomes peak, then it becomes peak, and then this becomes 0. After that, this becomes 0. So you can see that the current lags the voltage by 90 degrees. So this is the current curve. This is the voltage curve, and that's the current curve. Okay, so drawn. Now, what is the power? Power would be V into I. Each and every point. Then if you take this voltage and multiply that by the current at the same time, then I will get the power at that time. So I am going to draw the power graph now. For that I am going to use blue. So this is power. I am going to use the same axis to plot the power graph. Okay. So you see that this is 0, this is some value, but when you multiply these two, then power must be 0, right? Because anything multiplied by 0 is 0, so this must be 0. But see here, and as time increases, this is positive, this is negative. So positive multiplied by negative value will be a negative value. So more negative, it happens all. You can multiply all these points, but then you will get negative values for all of them. Okay, but then you take this point. This is positive, and this has become 0 now. So this will be power. If you multiply voltage and current, then power will be 0 here. So the power is 0 here, and then the power is 0 here, and in between it has become a negative value. So it has gone from 0 to some peak negative value, and then it reduced from that negative value, and then finally becomes 0. So that is what it means, right? So in this, so it starts from 0, ends with 0, and in between it has negative values. Okay, this is also a sine curve. We saw that it was sine 2 omega t, right? So this is also a sine curve, but then this is negative here. The power graph will be this. Okay, this is the power graph. Okay. Again, you take this part. This is positive. This is also positive. This is positive. This is positive. This is positive. So this must be positive in this. The power must be positive in this range. But then you come here. This is positive, but this is negative. So the power must be 0 here again. Okay. So it starts from 0. It has positive values and then comes back to 0 again. So you see graph of the number like this. The power graph. Something like this. Okay. And the same logic holds good here. So it's like that. Okay. And same thing here. You can see that this is the pattern is repeating. So what is average power? Clearly it cancels. You notice it. The power you have here is negative. The power you have here is negative. This will cancel with that one, and this will cancel with that one. So the average power over a cycle will be 0. So that is what you can infer from this and see from this graph. But this was not the case with resistive circuits. The resistive circuits is always positive. So start from 0, went to positive peak, became 0. Then went to positive peak, became 0. Went to positive peak, became 0. It was always positive. So you had a net power, the average power for that graph. But here, if you calculate the average power, it becomes 0 because at one point it is positive and negative, and the another point is positive. So finally, the average power in this is 0. So I hope you understand this part. Now let's do example 7.2. A pure inductor of 25 millihenries is connected to a source of 220 volts. Find the inductive reactance and the Rms current in the circuit if the frequency of the source is 50 Hertz. Okay, so what is given? What is given is it's a pure inductor, which means there is no resistance in that coil. Okay? So pure inductor, L is equal to 25 millihenries. Millihenries, that is also equal to 25.0 into 10 power minus 3 henries. Okay? Or 2.5 into 10 power minus 2 henries. Is connected to a source of 220 volts. So V is equal to 220 volts. I've told you already that when they say that V is 220 volts, which value do they mean? They mean that this V is RMS value. Always, when they say that you're connected to 220 volts power supply, then it is always RMS value. Okay, so this is V RMS, always. And find injective reactance and Rms current in circuit if the frequency of the source is 50 Hertz. Okay, so the frequency is given. Frequency is given as 50 Hertz. So let's see frequency of the AC voltage, and they want you to find RMS, IRMS. I don't have to mention. Okay, we don't mention anything. This is RMS. IRMS is what, and what else is asked? Inductive reactance. Okay, they also asked XL is what. So this is what they asked you to do. Okay. What is XL? XL we saw as omega L. Inductive reactance XL was omega into L. And what is omega? Omega is 2 pi F and L. Okay, this is omega, this is 2 pi F. So XL is effectively 2 pi F L. So 2 into 3.14 into F is 50 into L is 25 into 10 power minus 3 or 2.5 into 10 power minus 2 ohm. Okay, I told you the unit of reactance, inductive reactance is ohm. Okay. Now, so this is 100, that will, you will cancel that. 2 into 50 is 100, that will cancel with this 100. So effectively XL is going to be equal to 3.14 into 2.5. So 2.5 into 3.14 will cancel. So 3 times 2.5 will be 7.5, and then there is a little bit of that. So effectively it is slightly more than 7.5. The answer given is 7.85. Makes sense. It's equal to XL is equal to 7.85. Okay. Yeah. Next, what is the Rms current? It's easy. So, what is the current? Current will be equal to I is equal to V by XL. Right? Okay. How does this come? Well, we saw that I was equal to Vm by omega L into cos omega t, something, right? Minus this. So Vm by omega L was I, so your Im was equal to Vm by omega L. This is your Im, right? Okay. So then what is IRMS? IRMS is equal to Im by root 2, which is equal to Vm by root 2 into omega L. But what is this? Vm by root 2 to omega L. Vm by root 2, that is equal to Vrms, right? And that divided by omega L is XL. So you get I is omega XL. I is equal to V by XL. So simply V is 220 volts divided by 7.85 amperes. Okay. You can make a guesswork. So if this was 10, if it was 10 ohms, then it would have been 22. But it is less than 10, somewhere around 8, so it must be more than 22. So if you, the answer which is given is 28 amps, which makes sense. It should be more than 22, so 28 amps makes sense to me. Right. Okay. So use the log tables or whatever you find this, but intuitively you can see that this 10 should be 22. It's less than 10, it should be more than 22. So 28 makes sense to me. Okay. So that is how it is.